So in the previous video, we talked about one of the methods used to separate amino acids from each other, and that was paper chromatography. All right, and essentially what happened there is you dab your mixture of amino acids on a piece of paper, like filter paper, and you let a solvent run up the length of that. And essentially the types of amino acids that are more polar travel less, don't travel that far. The ones that are less polar will travel farther. And you can end up seeing, however far something travels is going to be specific to that particular amino acid. And so you can end up seeing what types of amino acids are in that mixture. In this video, I want to talk about probably a more common method for separating amino acids, which is electrophoresis. All right, and this technique called electrophoresis is not just used for separating amino acids and proteins, but it's also used very commonly with DNA, which is a topic that we'll be getting to a little bit later. So essentially, how the big difference between paper chromatography and electrophoresis is the property that causes things to travel different distances or to travel at all in paper chromatography is polarity. All right. In electrophoresis, the thing that causes molecules to move is their charge. All right. So recall that for amino acids, the charge on the molecule is going to depend on the pH of the solution that it's in. All right. So for example, there are 1, 2, 3, 4 different types of charges that could exist on this molecule depending on the pH. So what happens in paper electrophoresis is you take a strip of paper and you dip one end in a buffer over here, you dip another end in a buffer over here, and so the buffer has a specific pH. All right, so if we wanted it to be exactly pH 6, it would be pH 6. You can modify whatever pH you want this buffer to be, your paper is already pre-wet. All right, so since it's flat right here, there's not really, and it's already totally soaked, there's not a reason for this solvent to move in the way it did with the paper chromatography. But what makes this different is that in this buffer bath right here, you place a positive electrode, and in the other bath, you place a negative electrode. All right, and the thing about charges is that if you are a positively charged molecule on this sheet of paper, you're going to want to travel towards this negatively charged electrode. And if you're a negatively charged molecule, you're going to want to travel towards this positively charged electrode, meaning you're going to travel towards this buffer bath. All right? So depending on the amino acids that are in the mixture, some of them at that pH of the buffer might be positively charged and some might be negatively charged. And some of them might be completely neutral. All right. So again, if something's around a pH of 6 or has a isoelectric point of 6, and these buffers are at a pH of 6, an electrically neutral molecule doesn't have any reason to move in either direction. All right. But your positive molecules are going to move this way. Your negative molecules are going to be this way. And if something were to have, for example, a +2 charge, it would move faster than something that's just got a +1 charge. Okay, so this would be like a top-down look at paper electrophoresis. Here we would have like a beaker or something containing a buffer. So here we've got another buffer, and this has got a negative electrode stuck in it. This has got a positive electrode stuck in it. And this is a strip of paper that's spanning that gap. All right, so what you're going to want to do is you put your original spot or your original mixture. You know, it's like you would have your amino acids dissolved in water, for example, and just add it to the paper right there. And anything at that pH, anything that has a negative, all molecules that have a negative charge are going to travel in this direction. The positive molecules are going to travel in this direction. And in the end, you would end up, so once things are done traveling, you turn off your current and you take away your paper, and you might have something like this. All right. So if this were to be if the buffer were to be at a pH of 6, all right, glycine would not move at all. And the reason that it wouldn't move at all is that its isoelectric point is 6.0. So at the pH of that buffer, it would be completely neutral. It wouldn't have a reason to move towards the positive electrode or the negative electrode. However, something like aspartic acid, all right, its isoelectric point is 2.8. So if you have the buffer at 6.0, then at that pH, aspartic acid is going to exist primarily in this form right here, all right? And because of that, it's going to have an overall negative charge, all right? And because it's got an overall negative charge, it wants to move towards that positive electrode, all right? So conversely, if we had lysine, all right, whose isoelectric point is 9.7, well, 6.0 is less than 9.7. 6.0 is more acidic than 9.7, which means that it's going to exist primarily in this form right here, where both of the amines in the molecule are in their HA form rather than their A- form. So if you look at this molecule, that's overall a positive 1 charge, and therefore it's going to want to travel towards that negative electrode. So this is a fairly simplified example. If you had each of the, since if you look at all of the amino acids, you see most of them have slightly different isoelectric points. You're going to have different amounts of separation when you run this technique. All right. And so again, electrophoresis is a technique not only used for separating amino acids, but it's also used for larger proteins and nucleic acids, and we will talk about that more when we get to nucleic acids.